Okay, welcome everybody. This is the MS in Architecture Computational Technologies program. I am Pablo Lorenzo Iroa. I'm the director of the program, and today we're going to be having our first summer lecture series by Professor Shai Yeshayahu. The MS in Architecture Computational Technologies program has a series of discussions during the fall, spring, and summer sessions around the issues of what I denominated informed actualizations, from artificial intelligence to physical computation. The MS in Architecture Computational Technologies lecture series aims at discussing research framed by invited guest speakers and focuses on architecture expanding relationships between science, technology, and cultures through innovation in algorithms, simulations, AI, robotics, robotic fabrication, and materials. The lecture series discusses alternative means to understand the dialectics between the ideal digital and the physical digital. Within our architecture of information, AI, robotics, and materials are thought as actualization interfaces, therefore understanding information flows and their actualizations as architecture. Today, as I said, we have the honor of having our guest speaker, Shai Yeshayahu. Shai is currently an assistant professor of interior design at the Creative School in Toronto, Canada. He is the co-founder of BERS S+, a research-based collaborative practice using perceptive tactics to assimilate the impact of ancient, local, and emerging bodies of knowledge on design making. The collaborative has designed, fabricated, and mounted several installations and completed commissions projects, both in Canada and abroad. Currently, the collaborative is looking to how technologies and knowledge-oriented models inform the architecture of interiority. So it is a great pleasure introducing you, Shai Yeshayahu. Just as a personal note, I know Shai for a couple of years, more than a decade. We did together the Acadia 2010 conference at the Cooper Union, which was a groundbreaking conference, and we also edited the conference proceedings. So I know Shai for a while, and I know his interest in computation and his current interest in robotics. So I thought it was a good idea to invite him in the context of our MS program, and to also discuss the possibilities of what we're doing in relationship to information flow. So welcome, Shai, and it's a great pleasure to have you here with us.
Thank you, Pablo. It's really it's great to be back. I think it's the same group that we did the workshop with, right?
Yes, exactly.
Yeah, it's fantastic to be back. Hello, everyone. It's first being an alumni, I have to kind of say it. It's kind of coming back and lecturing. So it's always it's like a great energy. And to support the MS in Architecture Computational Technologies program that you guys are taking, which I think is one of the most cutting edge sort of like programs, or at least in themes that are really prevalent to our times. So you are engaged with the most current of current, sort of to speak. However, despite of this online platform that precludes me from inhabiting your physical space, although I think none of us is in a physical space, I have thought a lot about this condition. Although, many believe it's okay, I don't believe as such. At least for me, it is not, because in some very specific way, this lecture is given by me, or at least intended to be given by me, in isolation, while all of you are collectively discussing idea as a group, or soon will be discussing, I guess, because you are on your summer vacation. Or maybe because the space of lectures in general have changed the ways we experience or encounter knowledge. And I want you to stay with me on that thought as I seek to explain the kind of environmental, social, and cultural shifts conditioning the ways we gain skills or develop tangible practices. In this regard, Malvin Kranzberg, a historian of technology, who explained that technologies are neither good nor bad nor neutral, has triggered the specificities of this talk. He pinned the condition of our spatial definition in ways which I have come to recognize as computational acts. These computational acts originated millions of years ago, and they are not features from the arrival of the cell phone or microcomputer, not even the launching of the first geosynchronous satellite. And do not misconstruct this statement. Each of those debuts are extremely important to our design discourse. Yet, the narrative of computational acts centers on a set of bones named Lucy, after the song Lucy in the Sky of Diamonds, Lucy in the Sky with Diamonds, by John Lennon, which was first performed by the Beatles and playing on the radio when paleontologist Donald Johanson was celebrating his finding with his colleagues. Lucy's bones evidence that humanoids are the first among our sapiens lineage to become bipedal and fully digital. What that means to us in the design world is that mobility holds a superpower for all humanoids and perhaps even robots. That superpower started with the development of long thumbs and the ability to touch the other fingers, which in turn allowed us to firmly grasp, manipulate, sense, and control the things we find and shape. Furthermore, being a bipedal surrenders us with the ability to move in an upright position and to walk long distances. This ability provided a wider field of view that helped to scan the landscape around, leading to the recognition of environmental patterns. In 3.2 million years, Lucy's kin learned to decode, code, and recode Earth's surface. They first navigated in the savanna, and then they learned to reproduce Earth bounty as they move across continents. By the year 10,000 BC, roughly 12,000 years ago, Lucy descendants developed the first sedentary system that we now define as husbandry. Husbandry being cultivation of crops and the animal breeding, which is also the rationale that propelled the invention of the room. These rooms became cities, empires, and economic hubs that led to the emergence of the global city. At every one of these stages, social, cultural innovation gave rise to advanced technologies that shaped and formed the characteristics of the computational being, or the computational acts into being. This computational being has roamed Earth progressively, programming tasks that now a computer is able to decipher with ease. In this context, I will argue that sapiens are computational beings that in less than 500 years advanced light from candles to kerosene lamps, electric light bulbs, and to solar panels. Transportation methods from horse-powered to steam-powered locomotives to electric trolleys to gasoline-powered automobiles and electric power vehicles. Communication systems like pictograph on cave walls, alphabets, books, telegraph, phones, and apps propelled by knowledge and technologies. As you can note, in less than 25 years, we have become avid miners of data, capable of mixing and matching knowledge that enable us to experiment with technologies. As computational being, you and I have reached a moment in which we can go back in time to understand the different technological atmosphere we have produced and to grasp the spatial interest each of these technologies serves or served. We can see how applied knowledge produces different circumstances. And if we look at the history of our design processes, we can realize the duration of time it has taken us to get here. Hence, the question or questions that we are facing is not how did we get here, but how did we go, how did we proceed, how do we proceed from here? Because it is evident that in less than 50 years, we have arrived at a digitalized condition that has radicalized our design practice. In less than 25 years, the computational beam, in tandem with social cultural aptitudes, has evolved into a manifold of modalities, ways of acting and generating multitudes of solutions. In my case, as the system of communication evolved, so did the focus on ancient, local, and emerging knowledges. And this impact will be illustrated through three projects to render a very provincial argument about the relationship between the morphogenesis of technologies and design thinking. It is a kind of a self-reflective tool, a tentative approach to look at innovation as an essential medium that in return, or mediums that in return are helping me to consider a range of circumstances for design thinking. Although the projects are scattered in time, they correspond to a specific mindset that I would like to discuss. At -1 plus 81 was completed at the turn of the century when smartphones were not so smart, and when video streaming, social media, big data, and cryptocurrency were not as prevalent as they are today. H9 was realized at the cusp of the digitalized world, relying on computational workflows and CNC technologies to realize parts of its interior. And lastly, the robotic zigzag, work in progress, that looks back at challenges from 100 years ago to inform a robotic art. So I begin with looking at ourselves from a distinct point of view to allow us to really understand a localized condition from multiplicities of views, not just from what we see on Earth or what we typically see as we sort of like zoom in the city fabric, and then you're seeing that kind of like a plus on the left side in sort of like in isolation from the city, which is not the condition anymore of this fabric. Nonetheless, on the ground, the prevalent condition was a lot of use of concrete to laminate the ocean front or the hillsides that faces the ocean to avoid erosion, which was a solution that seems a bit odd at the time. We also looked at satellite patterns that were available for us, amplifying specifically here in '96 the phenomena of the El Niño, in which warm water starts to approach the coastlines, the Pacific coastlines, creating multiplicities of effects in terms of drought, rains, and so forth, affecting the region. So for us, you know, we'd like to look at things in ways that helps us to understand or plow through what are the important things. So we are building a certain matrix that were interesting to us to look at in terms of forces that have to do with technology, economics, sociolinguistic, and then seeing how they fit into these bodies of knowledge that sort of exist, and how each one of them has a definition within those bodies of knowledge, and constructing this matrix with a bounty of ideas that could be brought into what we want to amplify. And out of those, there are only specific ones that begins to inform the making or the doing or the thinking about the design. So we constructed a matrix that begins to explain a evolution of a typology, and then the breaking down of this typology into site, circulation, and landscape, bringing all of these elements together to create an object, an optimized object that has ways to look beyond itself and also have a way to sort of like center things around itself as well. So I'm going to focus on the area where the skirt was first treated, and the idea for it came from Machu Picchu. It's kind of like the ways of doing terraces because of the topography of that specific site. And we thought it would be sort of like interesting to insert that as a pathway that leads from one place to the other, from the house into the ocean. We began to carve the hillside, and we found a material that is a geotextile, a smart material, synthetic, that prevent erosion. And it works in tandem with vegetation. So we created essentially a substrate to allow for vegetation and this synthetic material to work together to create an ocean front that is predicated on the unit, the house itself, to be occupied and livable. Otherwise, the entire skirt also dies with it as well, because it's contingent upon the users and the recycling system that then feeds back into this skirt and allows the vegetation to stay alive, especially in drought time. There were other features that were sort of incorporated into this idea in terms of natural ventilation, so the passive approach to sustainability, and then the digging of a well that allowed for extraction of water at times when water was at scarcity. Some pictures of the interior of the house, or exterior and interior, sort of negotiating boundaries, which I don't want to discuss so much. And then the object, the house itself, and then the relationship to the city, relationship to the ocean, where am I coming from and where am I going to, I think becomes sort of like an internal dialogue and an external dialogue within how the house was conceived to act or to perform. At Hangar 9, which was a music venue in Carbondale, Illinois, Midwest America. It was a town where I was teaching at the university there. A storm that, I think it was a tornado storm that came by, basically lifted up the roof of this building, rendering it completely obsolete, not up to code, and not even able to be sort of thought of as kind of like an approach that looks at using the existing to make something new. That was not possible. The entire building had to be demolished, and we had to sort of like, because of this opportunity, we wanted to think about what else can we position in this site and how we can play with the intricacy of the program. The program had three elements, essentially. The outside, the beer garden, as they call it, the music venue, which is sort of like on the extreme left, in the plan on the left side, it begins with the beer garden, the music venue, the stage, and what opposed to it is kind of like a dance floor or a place where spectators could kind of habitat, the entrance zone, and then the bar that kind of parallels to that. And then we were able to add a mezzanine level without adding an additional code complication into the mix of things, because when you add a second floor, there is, depending on how you do this, and we did it in such a way that it was not really a floor, but a mezzanine, and it put us in in a place where we can really not comply with such strict codes, especially when it comes to fire and occupancy. So within this building, we looked at a typical steel frame and how we can take this typical steel frame and translate it into a new vocabulary or compose something new with that same vocabulary. It's kind of like we have a kit of parts. How can we think with this kit of parts in ways that serves us rather than conform to what the kit of parts sort of like gives us? And we, within that, we developed a ceiling, an acoustical ceiling that was part of a response to the musical venue to allow for an acoustical barrier within the space or to amplify the acoustic or to improve the acoustics of the space. At the same time that it began to generate this, there's an animation there that is missing, but that's okay. It was a question of performance and this idea of how do you allow for the space to function while music venue is taking place and sort of like controlling the acoustics to some extent. So what you're seeing in the center, that sort of like mesh, that became sort of like a ceiling, and the ceiling was sort of like optimized to work within tandem in the section. What you're seeing is the stage on the right and the mezzanine on the left, and kind of like the viewing platform below that. Here is that animation. So we kind of like simulated, sound from a source, throwing it towards this the ceiling, the geometry, and seeing the amount of reverberation that is being sort of like giving back to us and adjusting the geometry based on these readings. Ultimately, we developed a parametric model that allows us to understand the constituents of this ceiling from the surface into the sort of like the divisional isoparm or the location of the center points or the junctions. After that, that third sort of like graphic on the top is this sort of like the length of cables that need to suspend the ceiling, the geometry itself broken down into triangles. Those triangles then had a certain thicknesses into space. And then lastly, the connection, which you see sort of like in the middle panel between four struts, was developed around a four-way connector that allowed us to sort of like inject this ceiling or to build this ceiling in the space and for it to provide a blanket that kind of ties the two spaces together at the same time that it's providing an acoustical solution to what is being addressed as part of the programmatic need of this build. In the robotic zigzag is essentially the research work in progress that I'm currently working on. It takes really the zigzag chair, a very iconic chair, and try to rethink the making of it, which has been done extensively by Rietveld himself, but also by contemporary people like me in this sort of like century and past century, but late past century, where this chair has become a fascination as to what material can represent it. And for me, it becomes a fascination of what technology can make this chair and whether robots could take the challenge of folding something that has a material that has a continuity to it and is not broken down. So looking at this chair, I began to compare and contrast it to sort of like chairs that are sort of like not only iconic, but also had a similar mindset, continuity, flat pack, I think the Umbra Tokyo by Eileen Gray is sort of like almost like a flat pack. You can kind of flatten everything into one sheet, and it becomes sort of like that. And you can cut that chair out of one sheet. And then Larman, Bits and Parts, a complete 3D printed chair as one piece. So I think that gives the understanding that continuity is something that was important for Rietveld in his entirety of his thinking and philosophy, the continuity of space or the infinite space, which was always at play in his design thinking. Looking more carefully at the construction of this chair at that time, I think it's clear that there was a certain constraint, not by just looking at the chair, but looking at the array of work that Rietveld have produced as a sort of like continuous experimentation with the way in which the zigzag can manifest itself through materials, through combination of materials, and through the technologies that were available at the time to achieve sort of like something that looks seamless. Although the first part that is made out of wood looks seamless when it's constructed, it's still made out of single parts that are attached together. The tubular one is sort of like one of the interesting proposition for it. It kind of, for me, it really represents continuity or infinity in much more clarity. But it's sort of like it's the absence of the planes, and it's more about the delineation of the lines in space, and then allowing a certain planes to exist there to allow for, the seat and the backrest to kind of, become what they are. But it's more about the construction of, continuous tubular form that then gets additional materials layered into it. Jorman, with his RoboFold, I think has introduced a complete different thinking about how we look at patterns and how we look at techniques in which robots use to sort of like attach themselves to this pattern and move about a particular axis in space to allow for this folding to occur. What you're seeing here are not really full-scale chairs. Their chairs are about this size. They're not that big, but it was more of like a proof of concept. And can robots really fold the chair? And I think that sort of like exemplified that it is that this possibility is very much attainable. For me, looking at all of these arrays of thinking and techniques and understanding about technologies and what we do, what we currently do with them, or what we did with them, it was pretty evident that the robot will be only one piece within this process. There were other additional things or technologies that will have to come into place to be able to accommodate for the making of what I wanted to, or what I wish to explore, which is a continuous surface that gets folded by a robot and allows for the creation of a zigzag shape, not necessarily a zigzag chair. So the shape itself is of more interest to me because of a particular constraints that I'm going to get to in just a second, that has to do with a sort of like a uniformity, an ability to create something from a singular material that does not require an additional assembly to it. So the product can be produced by virtue of creating these sheets, sort of like the strips. When you unfold the chair, it becomes one strip divided into 4 segmented parts. Initially, I was thinking of a jig, sort of like a bed that the robot will perform over, and the bed will have a certain adjustability to it, so the robot can kind of move around it. That has proven not to be so effective through simulation, because it required a robot to move quite a bit around the table. So it was not really, it did not serve me in the way that I thought it could serve me. It actually created a bigger problem because you never have a fixed bending edge. Therefore, every time it requires a new adjustment or new calibration for every fold, and that kind of, it might achieve the zigzag shape, but it much more in a much more complicated manner. That does not really, I thought it does. Maybe there is a easier way to produce this. At the same time, I was looking at the robot and how the robot environment and the restriction that exists around it. Looking at what OSHA defines, areas of zones of safetiness around the robot, and what other kind of defines as kind of the areas in which the robot perform in. So you can kind of see the two analogies between how an institution represents this diagram and how somebody from the industry who is particularly interested in the robotic reach. Where is the reach of the robot end, and where does it begin, and how do I work with these constraints? The bending itself, I'm just gonna, I think it's important that we're kind of like cover this, is a very complex and also very old-fashioned techniques of either a bend box or a die, like we see on the left side, that you have the metal pattern, and then a machine sort of like pushes the material into it and creates the shape, or a hand tool that kind of creates that. And then the diagram of, what really happens around bending, particularly around the edge, and where is that material distribution occurring, or how is it even occurring? In terms of just, if I keep bending a metal, at one point it will kind of break and stretch out. So where is that break point? At the same time that I was very curious to understand the spring back. So when you push a metal, there is always a pushback. The material kind of has its own memory and wants to come back. And that was a factor that became really interesting as I am trying to fold and reach a certain degree, and I'm not able to do so yet because you need to push more to be able to get less. There's about 10 degrees. If I'm pushing 80 degrees bend, eventually I'll be getting something between 70 to 75. There's always 5 to 10 degrees that are somewhat lost because of the material logic itself and how it behaves. So I looked at a way in which the pattern could have a little bit more of a logic on the bottom left, perforating the bent line, so to provide a relief, so the robot does not reach its payload limit, before anything within this experiment could happen. So I opted for subtracting material to allow for less force to be able to be applied, in hope that the experiment could really benefit from that. At the same time, I began to look at the 3 jointry areas, the angles that exist there, and the complication that brings within it, in the sense of coding a specific system of angles and understanding where does one begin and where does one end, that really has to do a lot with how the robot is working around the chair or around that sheet of material to be able to create essentially 3 bends, which are seemingly fairly easy, yet the challenge of producing a 135-degree bend can only be done on an up push as opposed to a down push, which is those 2 techniques that I'm sort of like exploring within this process. One is pulling the material with the robot or pushing the material up, or the other one is pushing the material down. And that has to do with the specific angle that I want to create, and then working around a particular bending edge that has to be calibrated for this. So within this process, initially, I thought about this in doing it with vacuum, with air pressure, which was simulated very easily in this, or at least it gave the understanding that this is very much feasible. And while this sort of like robotic action is taking place, there is various parameters that are being looked at in real time that has to do with air pressure, monitoring the air pressure. There is also a digital signal between the robot and the computer, allowing for on and off positioning. And then looking at 2 locations of temperature to see a variation of temperature on the material while the bending is taking place, and then timestamps on all of these things. And at the same time, I was hoping to wire MPU sensors. Essentially what they do is they give you a location in space with 6 parameters. So you have a point that has essentially XYZ is multiplied. You have X1, Y1, and Z1. You have a set of 6 parameters for each point in space, which is essentially 4D space, kind of like defined within this set of parameters. And then ultimately placing an IR camera specifically on that seam line when the bend is occurring to not only see the variation in temperature, but also maybe to capture the variation in the material, what occurs to the material when force is applied on it, and how the temperature change should be reflected within these readings. It's kind of like the entirety of the board that I put at one stage to look at how essentially for me, it's really more about the feedback loop that kind of goes back into the left side pattern template, and how the reconfiguration of that pattern, or the rethinking of that pattern, or the rethinking of the code will then re-inform the processes in which the robot will have to go about to make this zigzag shape. So this sort of like two animation. One, there's kind of like distinct points of view in terms of showing how 2 robots could potentially collaboratively work together using vacuum suction to create this folding. I'm not able to work with 2 robots. We don't have the capability in the lab to synchronize between 2 robots. And the air pressure has proven to be extremely complicated to achieve enough suction force for the robot to be able to, it's not the robot, but it's the suction cup itself to stay in contact with the material while the robot is trying to pull that. What happens is that there is at one point in the beginning that there is a complete disconnect. There is no ability for air suction to really hold there, which means that the air suction pattern or it has to be redefined or rethought of, and then the equipment that is required, is the air the air pressure, the PSI, needs to be very constant to be able to produce a type of suction that will allow for this to happen, for a folding using vacuum. At one point, we had a UR robot in the lab, so I was working a little bit with it to sort of like see if I can fold with this small robot. I think this was a quarter scale template of the chair. I worked with eighth, quarter, half, and full scale in 4 different scales with 3 different gauges of material to see where is the give and where is the failure. Where is the opportunity to actually bend, and where is the opportunity to actually fail? Part of this entire experiment that I ran, it was first ran with the suction cup, which I don't have the video with me, and then it was ran with the clamping tool attachment. The clamping did produce, was able to bend, and there were few parameters that sort of like enable me to understand that there's got to be a certain level of precision in terms of how far or how close the exerted force is to the center of the bending, which is the line of bending. The further it is, the least intricate the bend is, and the least control it is. And the closer it is, also begins to represent a particular problem, especially as you see in this image, the one on the left, that if I bring the robot closer, then there is a collision with the edge of the table. So there is sort of like these nuances of how close can I get to the material, or how far can I be from it and still produce that same effect. I want to talk a little bit about Rietveld and this idea that in 1917, this guy was really thinking very eloquently, not only in terms of carpentry and how to put jointry together, but he was also fascinated with materials, with representations, and sort of like a creation of a chair that, as you can see from the sketches on the right or drawings from the right, they are patterns with some sort of a relief form on them, or sort of a thing like that, that allowed him to vacuum form this chair in 2 shapes and then kind of like connect them together. The tubular things at the bottom, and then how he works with this one singular material to create this one unique shape. I think it becomes really fascinating to understand that the same things that we are thinking today, how to take one pattern, one material, sort of like consistency, and use that to create one thing with it without the need to connect. Although he does connect 2 funny triangular legs at the bottom. But I think aside from the legs, it's the body of the chair itself is where my fascination lies. I stumbled upon this recently, looking at some lectures about Rietveld and his kind of like thinking, theoretical thinking, or his kind of like technological thinking around material and around technologies that will help him to construct those forms or to realize his ideas in ways that are, not singular, but in multiplicity. And it also begins to suggest that, the computational being or the computational thinking or the computational acts are the ones that are driving us, whether we are conscious or not of them. Lastly, I want to sort of like discuss or leave us with this teaser about, the duck that Jacques de Vaucanson created, the pooping duck in 1739, which was then the most advanced robot. What we're seeing here is a replica of it. But back then it was the most advanced robot. And after 282 years, we are facing now the Boston Dynamic robots, which has almost, near human capabilities in terms of mimicking us with extra powers, of course, kind of built into that machine. But nonetheless, seeing the contrast between what has been achieved in the past versus what has been, where are we currently within this technology, also helps us to understand how the compression of time, especially at the beginning of the 20th century, allowed for a boom of knowledge to surface up and to inform us about our abilities and our ways in which we can engage with design and with making. So I want to leave you with, on the left, the traditional way of bending that I kind of spoke about earlier, in which, a robot, some sort of a robot kind of pushes a material into a die and then create its pattern. While on the right side is me still working with simulation and trying to understand a method that will allow me to not only bend, but also understand the limitation in terms of how much angle can I really bend a material using a robot with essentially a jig that was created by me. It's kind of like a bending edge that I rigged up so I could work around it. As you see on the table, it kind of cantilevered out of the table so I can achieve above 90-degree bend in one direction to then allow me to, for that to spring back into the 80 some degrees that I need or that I want to achieve within this kind of like zigzag shape or this code that I have defined for myself.
The forces applied during.
Thank you.
Thank you, Shai, for your presentation. Very interesting work, and I'm actually glad that we are having you in the beginning of the term, because you describe several of the issues that the students are trying to activate in the relationship between what I call in the lecture series the digital ideal, and then what happens at the fabrication level, which is a differential that most of the time, I mean, one of the things that I always refer to and that I actually have been very voiced about is that I think that because of the type of if you want, ideology in which we are in today that privileges the image over other things, I think that in fabrication we have that problem that most of the time architects think in terms of fabrication as an image of the ideal digital, rather than thinking on the differential as an opportunity to expand on that problem. I recently wrote an article about it, so and also we're working with metal, so it's like perfect your lecture for the kind of project that we are actually starting this term. But I would like I don't know if students, and also we have Nelson here that teaches with us, and I don't know if anybody wants to jump in and ask Shai or make any comments over the lecture, but I would like the students to choose. I wanted to ask a question because I need to know how they're thinking about it. So this is it's not optional, let's say. Until now it was optional. Now starts not being optional. I need to see, especially because the last weeks and the last semester we had some difficulties to activating the problem. We were working with clay 3D printing, And we were delayed with the Fab Lab and whatever, but at the same time, I think the students are getting used to understanding the complexity of physics in relationship to the model. So I don't know if Nelson or the students want to jump in.
I'm just gonna ask like two simple questions. The upward and downward bending, I didn't really get the difference between both. Like what's the difference between bending downwards and upwards? And when you were saying that there was a problem with the suction gripper for with the air compression, so do you mean that this is fixable by like if you had a stronger air compressor, like this is the problem? You just don't have the inventory, but.
That's a good question. I think these are all the challenges that once you are in the lab, you begin to kind of see. So you're asking there are two questions. So I think for me, it's not a question of, we have about 150 PSI, and I think that's just should be plenty. However, suction is also measured by bars. And that's where it becomes really, extremely complicated in terms of grasping, but it has a very particular, essentially it's like a G-force. So the more of that you can achieve, the more you'll be able to pull with. So with what I was using actually a Venturi valve. So a Venturi valve takes air pressure and translates it back into suction. So there's probably something there that there is a certain amount of energy gets lost within this Venturi valve. And then I think the surface, how much area of suction can, like the maximum area that you can get to do this. I believe that if I increase the area, probably there would be a possibility for the robot to do the bending. More so in the pull as opposed to in the push. And I think this is, I don't know myself either, which is better. All I know is that with the push up, I can achieve larger degrees of bending, while in the pull down, I achieve a less degree of bending, but it gives me the ability for the robot to work up and down in both directions and not just in a singular direction. But I can't really answer you whether this is better than the other. I think that's also, it's part of that research. One of the question is pull or push, which is better, sort of to speak.
Okay, thanks, Shai. Nelson or Salma, Farah? Nelson wants to.
So I just want to congratulate you on your work. I mean, the last case was just phenomenal.
Thank you.
Case study. The degree of, of care given to the specifics and the details. And I especially appreciated the systematizing of the protocol, which is, I mean, every time, especially if we're architects and designers, we tend to talk about things in poetic terms, but this is like when things get real, and you need to sort of become this kind of almost engineer-like systematic thinker to get to where you want to go, and to actually learn stuff, because learning is sometimes even harder, like taking lessons out of like what you were just discussing about the pulling, and it's a very fine line, and you have to kind of go through it. So I have a question. Have you ever considered trying to kind of I don't know how it would be possible, because you're working with robots and it's electrical. So, but because I'm assuming that if you're working with iron or steel,
steel. So essentially, that's what I have is steel. Yeah.
Okay, because either change. I don't know if you've tried to change. Have you tried to change to another material, like an alloy, like aluminum steel alloy, or have you tried still working with steel, but trying to get like a hotbed to get it to because steel expands. Right. You get it hot and it gets easier, it gets more malleable. Right. So have you ever considered that? Have you ever been able to put it in place? Or
yeah, I mean, I think that's kind of like the contention behind having these tools around that bending edge and measuring the temperature change there, which I think, but it's so minimal that I could, with my equipment, I could barely tell if there is one there. But yes, I think the idea is that if you have, first, if we could somehow change the molecular structure of the steel at that particular point, then we can make things easier. We could work with robot that has less power. Let's put it that way. I'm working with a robot that has a 10-kilo payload, so it's very little. So I'm working with very thin gauges. And I'm working with soft, sort of like steel, sort of to speak, because I know that if I go with something heavier, it's a failure right from the beginning. So I wanted to see the failure at the sort of like the thinner thicknesses of the material, the higher gauges, sort of to speak, to see where it begins to fail or where it begins to become successful. But this idea of hotbed, I think, yes, but then there is that kind of like budget limits of how much your grant has and where are you allocating this money to. So that perhaps could be the next phase of this, looking at bending, but now with an intervention of, into the material itself, or sort of like changing its characteristic to allow for the bending, and then kind of like bringing it back to what it is.
I'm sorry. Yeah, I might just add. That's called a phase change, actually. So that's what you want to get, because you change, you get anisotropic properties when you change the molecular structure due to temperature. It's thermodynamics, basically. So yeah, that's exactly.
Yes. Fantastic. Are you in Belgium, by the way, or just the background?
He's
I just found it. No, I'm in Paris. But I've been to the Atomium, and I'm a big fan.
Yeah, me too.
No, I mean, it's great that we are discussing this, because I think students, for the students, you have to realize, we were discussing this week, well, we're not really discussing, but I'm ordering the material that we're going to be working with, because we got a grant to actually work on the installation that we're working on. And I think that the students, they need to start understanding the alloy problem, right? Because I just ordered 3003 alloy for aluminum, and it's because I'm expecting a certain malleability, right, in terms of what Shai and Nelson are talking about. And that's a kind of not only meaning but knowledge, right? And I think that what we are talking about, what Nelson is talking about, and what we have been trying to activate last semester with shortcomings, is the difference between modeling in the computer, or even if you're not modeling, even with data, right? With data happens a little bit the same, right? Like in AI, to me, the current problem is that people don't understand what they're working with, right? They're not understanding the logic of the data that you're funneling through the modeling algorithm, right? So there is a disjunction between the data and the way the data is being modeled. When you're working with physical computation, or you're working with physics in terms of material, you have also the data of the properties of the material. And what, Nelson, you're talking about is the change in phase, which makes things very difficult, because you not only have the thing, right, but you have the time and the phase change in relationship to the outputs of the machine, but also the inputs and outputs of the environment where this is happening, right? So what Shai was talking about, the valve problem in terms of the bar levels, there is a competition between the environment where you're performing whatever you're doing and the bars that you're achieving through the suction, right? So there is like a pressure problem, which we also dealt with in a very little manner with the clay 3D printing, right? Like there is a problem of atmospheres pressure that plays in terms of how you constitute the clay. We did not really arrive to motivate that, but that was one of the objectives we were after. When in the material that we're going to be working with this term, I think that what we're talking about in reality is the definition of knowledge, right? And I want the students to think about it, because when Nelson says that we're used to architects dealing with poetics, that's to me a huge issue in a way, right? Because on the one hand, we have the cultural knowledge, right? That we can think about, literature, philosophy. But when you think about the people that were actually able to activate knowledge in terms of those disciplines, it's very different from just talking about whatever, right, in philosophy, or talking about or trying to do a poetry that doesn't activate the problem in language, right? I think with technology, the difference is that technology has to function, right? The meaning of technology is knowledge that actually functions. That's to me the definition that I like working with. And when Lenson says that you have to measure whatever you think is happening with what actually it is happening, is that what you are able to incorporate as knowledge. And I think that the problem of architecture in general is that we don't like, at least when we do images, when we do experiments in general, we don't like to have the accountability or the verification of actually what's happening at the knowledge level, right? And I think that that's what you need to actually go through if you want your fabrication to be successful. Otherwise, any experiment is whatever, right? Something is going to happen. But the question is, what is it that you're understanding and what's happening? Because if you're able to systematize it, that means that there is a knowledge that you're putting into motion. And that's, to me, where the project starts. So I don't know if you agree with that definition of knowledge, but that's, to me, what's happening at the cognitive level with fabrication that I think we're not working with yet.
Yeah, I completely agree, Pablo. I think there is a dissonance between the virtual and the real to begin with. Sometimes it's a big gap and sometimes it's a smaller gap, and we kind of have to figure out how to close this. And I think knowledge is the thing that helps us to look at these parameters, variables that are at play. Each case is very specific. And then how do we understand these parameters in this new context that they are being put into? Let's say using a robot to 3D print, I think brings a host of issues all together in terms of, are you taking a 3D printer and just putting the 3D printer on it and just kind of letting it print? Or are you controlling also, the nozzle with IOs kind of like on and off? So mostly what I've seen is a straightforward nozzle. You put it on the printer, you press on, and it just spits the material, and you're constantly printing, but there is no stop. There's no ability to do the stop yet. At least I have not seen it, which is fairly simple in one level, but I think fairly complicated when it comes to that 3D printer and ad hocing it into that robotic, or integrating it into the robot. This is one of the problems that my lab is facing in terms of not having these digital inputs and outputs that you can then use to control. Essentially, it's just like a switch. Now I have a switch, I can turn something on and off whenever I want to through a particular command within the script.
Salman Farah, I need you to make a comment or a question. No escape, in a way. I want, so Farah, I see you first, so you go first.
I agree when Professor Pablo says that a lot of, when modeling through data, I don't understand what is happening in those algorithms itself. And then from that going into fabrication, either 3D printer or clay printing, there are gaps that I don't understand, and I would like to understand them better.
So, but you see, so how, Shai, what do you think Farah needs? Because Nelson pointed out that you were systematizing very well, right? So that's one key, right? You want to add anything to what Farah is asking?
I think you need to really understand if it's 3D printer, you really need to, or 3D printer is printing, is that you need to understand the parameters that drive the 3D printing, flow of material, rate of flow, the heat, or whatever it is that the material undergoes before it gets squeezed into that tube, how much force is squeezing it, can I control that rate, can I change that on the fly? If you have like an adjustable knob, it's analog, but if you don't have a digital, you can make anything analog. So I think you need to understand what you need to control beyond sort of like I will call it the MakerBot printer, where you just kind of plug and press and it prints, supposedly. You need to really understand what's the logic that is driving the machine itself, and then understand really it's about material logic. It's really, for me, in 3D printing is really what material are you printing with, and how do you bring the material to the consistency that will allow you to extrude it at the same time that will also allow it to cool down effectively at the particular rate that you want it to cool down, so the next layer could layer on top of it. If you look at videos of people printing in clay, especially Ron Real, you see that he prints, and then bloop, everything collapses because the material does not have enough time to dry or to hold itself. So you have to print and stop to layer by layer, and it's a tremendous amount of time to do the print and stop. So it's really about how do you add an additive to the material, so when it touches air, now it can cure faster. I think it's a question of knowledge, as Pablo said, but knowledge in the distinct disciplines. Like maybe somebody who is a chemist needs to sort of like come in and explain to you some logic about materials and how you can hack these materials to give them the properties that will serve you at the end.
But since I'm glad that you're mentioning that, because the students actually went through that. All of them actually, they work very well with 3D printing, and then with clay they face exactly the problems that you're talking about. But I think that since we are in a university setting, we have to make use of the interdisciplinary problem, right? Like so, for instance, when I ask the question about the clay, right? I feel like you are not using the institution, the structure of the institution, because you could go and see who's like actually could be somebody that you could bother, like another professor, another student, an engineering student, right? At least when I was in Princeton, and that's what you have to be careful that there is, I think, a generational difference. We did not have anything, literally. We had the internet, but there was not, you could not search for videos of how to do 3D printing. We had to figure it out ourselves, right?
It was a library and books.
Right.
That's all we had.
And it was empty.
But also,
and they were never there.
And also, in my case, I never had any money. So it was like all ad hoc. I wanted to do things, and there was never the possibility. So I think that you have to really fight against the normal condition today, which is to be able to access a lot of things and actually take initiative and see what is it that you need. Because if we give it to you, I think that there is a problem there, because and I'm thinking about the alloy. I just gave you the alloy, right? And I say, well, we don't have time, right? But I say, damn, I'm already losing in terms of the pedagogy of the studio, because I need to order the material, and I already told them 3003, right? And I hate that, right? Why? Because you're not going through the process that I had to go 10 years ago when I was working with aluminum. And I feel like you are losing by me resolving the problem. So to me, one of the things the students are asking, yeah, but we need somebody to ask for this. I don't know, yes and no at the same time, because you have to identify what the struggle is, and you need to understand how you're within the conditions that you have, how you're going to overcome the struggle. I like, for instance, cooking when I don't have the refrigerator full. You know what I mean? Like I need to feel, I realize I cook better when I don't have everything. When I have everything, I follow the recipe, let's say, right? Like I'm playing the ratatouille thing, right? But when you don't have things, which is like a little bit the story of my life, that's why we have these things hanging there, right? You have to do it yourself, and I feel myself more creative when I don't have the resources. So I feel that the student, and I know the students, they come from different parts of the world, and you probably share with me the same background, but you have to be careful. To me, what we always talk about, the condition of choice. When you're choosing, you're already in a paradigm that is problematic. So how are you able to understand what is it that you need is already the question when the framing of the question happens.
And if I might add just two, I mean, seemingly small, but in huge things, design experiments. Design your experiments. You want to know more about a material, design an experiment to test something. You can sometimes test certain things at the same time, and sometimes you design an experiment for one thing and you get surprises, but design experiments. And also learn to ask questions. I like the way that Youssef asked the two questions, because they were right straight to the point about a subject matter that was very clear, but about things he kind of couldn't get together. You know, that's I don't want to rant here, but it's extremely important. You need to understand how to ask questions.
You're talking about design research as a methodology, because it is a scientific, it's considered
design research.
Exactly, design research. So Shai, who told you? Who did you go to? Who told you what to do? Actually, you know what I mean? Like if the students say, so who did you ask? You know.
I didn't really have anybody to go to other than the books and the internet. I think for me, it's a question of syntax. You have to, and what Farah or what you mentioned, about what feeds into the algorithm. So you kind of need to understand how to ask the question to be able to get a more wealthy response to what you're looking for, and then you're able to nitty pick through that at much more ease. So what I typically do is I begin to ask question. I begin to question Google until I found the particular vocabulary that the subject matter involves within it, because I don't hold the entire jargon around metal bending, which I now know a little bit more of. And then that allows you to then interject into your questioning of the algorithm, more specificities of vocabulary that you're using, and the response becomes, they come in much clearer. And but initially, when I did the research, what I discovered that there was a gap. This entire bending industry is like an ancient industry. They only work around the die forming thing, or they're working around a bend box. So there is a big robot that takes a big sheet of material, but it only does a bend that there is this much material left over the edge of it. So it's kind of like, okay, it's kind of like the same thing as fitting into a bend box manually and kind of doing this thing. And it's a sheet by sheet. It's never a continuous material that the robot works around to create something, and then you decide where you want to cut it. So those were the two driving forces for me that then allowed me to think deeply into this entire realm of bending, and what is the distinction between the analog bending versus the sort of like robotic bending, and where within robotic bending we're really not there, and how does the analog methodologies can help me to think around the end effector, because essentially it's really about what you're putting at the end of the robot that will help you to perform the task in more clarity or conciseness. For me specifically, it's the more area I can grab from the material, the better off I will be. And the closer I am to the edge, the more perfect that bend is going to be. Essentially,
I'm happy that you mentioned that, Shai, because that's one of the problems. When we did the Arizona Cardinal Stadium, we did the first stadium air conditioning in the world in the middle of the desert in Arizona. And we had to do, we actually went, that's why I'm interested in metal, because of facade systems and so on. And that's what we're going to do this term. So I'm very happy. It's like very precise, the timing of your lecture here. We were able to do what we were able to do because of Frank Gehry, right? Like everything goes back to even, I mean, I'm talking a long time ago, like almost 20 years ago, but we did after Gehry was able to do the Disney Opera Hall, right, in LA. And we were able to actually use the machines that they had to build to be able to do the bending that you're talking about, because it was a firm in Chicago that they developed a rolling mechanism. Like
Zayner, right? Zayner? When there's
no,
Zayner?
What was his name? Richard, I don't remember now the name. It's a huge company, robotic, everything roboticized. I'm talking the year 2000, right? And the difference is that we could take a single sheet in a roll and cut it, with lasers any way we wanted to. But the problem that we had in the Arizona Cardinals Stadium was that the insulation was already built into the panel. So they had to devise a way to roll the panel with the insulation inside the panel. So it was 2 metal pieces plus the expanded, the high density polyester, 2-inch thick, and we were having double curvature. So it was extremely complex, and we did 150,000 pieces, which 10% of them are double curvature. And we were able to resolve the entire envelope through that system. But it was exactly that problem that you're talking about, that they understood that if you do it with robotic arms, you have the problem that you're talking about, and that they had to develop the machine to actually do that. And that's when they were able to actually get, after that, they did almost all the stadiums in the US, just because they were able to figure out that technology. Then the other one that I can think of is Richard Serra. Richard Serra's pieces, right? He had to, the double curvature of the, they're gigantic, right? So he had to work with the manufacturer to actually produce those things at the industrial level. But yeah, Lenson, go ahead.
Fun fact. I remember seeing that project, how it was built in National Geographic, and when I was a third-year architecture student.
You mean the
fun fact, the Cardinal Stadium in Arizona.
I'm not happy with this. I was the main designer. I'm not happy. I thought it was actually
I think it's a good project.
But it was, the innovation was that. The innovation was the fact that it was the first double skin. And even today, there, if you think about digital fabrication, there are almost non-double skin insulated fabrication pieces. Most of them is only one laminar piece. So we innovated at that level only. The rest, I don't think it's
no, but I always found it interesting. I mean, it looks like a plant too. Like it has a proportion of a sort of cactus, and I think it was well thought of.
Yeah,
actually.
But Farah, I don't know. You see what we mean? If that makes sense, what we're talking about? Because I want you guys to think about it, because that's what it's all these things about bending, heating. That's what we're going to be starting with in the next 1 or 2 weeks. So, Yusef, I see the focus of your question, so I understand that you're already thinking in terms of the mechanism. Now we need Farah, Kavya, and Salma. Salma, a comment or a question? Unless Farah, you want to say anything else.
Thank you so much for your presentation. I don't really have a question, but just a thought, because it was interesting to see your work on the chair, especially that we had to work on a chair for the final assignment of one of the classes. And we kind of now understand the different challenges that we could face in terms of the choice of the material or the fabrication method. For us, we use the vacuum forming and then creating pieces and thinking about the assembly and the joints. And it was really interesting to see your process of how you thought about the material itself, and thinking about the mechanism of the bending and folding and how to use the robot now, because these methods have they exist for a long time, but how to think about it in terms of the technologies that we have now, and in a way computing the material itself and the bending to create the shapes that you wanted it. So yeah, that was interesting to see. So thank you for the presentation.
Any comment?
I was barely able to hear because I have somebody here at the house who's doing work, and you're probably hearing the humming right now. I'm going to try to connect through a headphone.
Yeah, I just wanted to say we're going to dinner now, so extremely happy to see your project, Shai, and meeting you, and happy to see you guys. See you next week.
See you next week, Nelson. Thank you.
Thank you for reminding me, Pablo.
Yeah. Kavya? So, Kavya,
I don't really have a question, but thank you for showing your project, and especially I like the workflow, the flowchart type of workflow wherein you're explaining the computational part and then leading to the angles, how you joined, I mean, through the joints. So yeah, I mean, the angle, the angled way, the way you executed it was really fascinating for me.
So they are both compliments in a way. I don't know if you heard Salma, Shai.
Were you talking to me, Pablo?
Yes. Did you hear Salma? Salma was also complimenting the work.
Yeah, she was talking about the angles, right? I made something out of that. But was there a question that she asked?
No, well, there were two comments basically.
Okay.
But anyways, I just maybe we can conclude because already we are extending beyond our normal time frame. But I thought it was a very interesting conversation and very related to the type of issues we're going to be working with. So thank you, Shai, so much for your lecture, and congratulations for your work. I really like the focus and the attention. So it was great to have you in our lecture series, and we look forward to see more of your work.
Fantastic, Pablo. Thank you for the opportunity to speak to the class, and I'm looking forward to jumping in, seeing what you guys are doing. I'm extremely excited to see what you're going to do with this 3033 whatever aluminum that you have. I think you just solved a part of the problem, and you, in a sense, created another one, sort of to speak. There is a constraint now, and you kind of have to work around it. I don't think that you will achieve something, and then you will make a lot of discoveries about maybe what could have been a more ideal material. Maybe not. Who knows?
Exactly. All right. Thank you so much, Shai, and we'll see each other soon.
Thank you all. Have a great day.
Bye-bye.
Thank you.
Students, please.